You are having the same value, so only that change is instead of the block, you are given a constant tangential force. In that case, what will be the acceleration of the mass? What will be the acceleration of that mass means, so here in this case, it is a constant tangential force means, then you don't apply that elevator formula, m of g minus a. It is a constant force is there. So that's why that T will be equal to 2 kg weight directly. That T will be equal to 2 kg weight directly. Here suppose in the previous case, what is the difference in between the previous one and again the present one? Here it is, in the previous one we have taken the block here. When the block is descending downwards, then the tension developed in the string will be changing. The tension developed in the string will be changing and it will be definitely less than that of the 2 kg weight. And suppose if at all it is moving upwards, then the tension will be that is greater than that of the 2 kg weight. But here it is a constant tangential force is applied means you have to directly take that T value as the 2 kg weight. That's why it is the TR is equal to I alpha. TR is equal to I alpha, 2 kg weight is directly taken, so 2 into 9.8 and R is equal to already we know 0.1 and it is the, so it is the I is equal to 0.1, alpha is equal to A by R and here that 0.1 will be cancelled and already we know this is nothing but the A is equal to 0.2 into 9.8, that becomes it is the 1.96 meters per second square because R is equal to 0.1. So that's why 1.96 meters per second square. Now it is acceleration is completed, that is for this problem, and thereafter now we are coming to this, that is the next problem. It is mentioned two masses m1 is equal to 12 kg and 8 kg. So here it is m1 is equal to 12 kg and the 8 kg. So in this second problem you are not given any figure. But even then from that given data you have to draw that figure because you are mentioned it is the Atwood's machine. Two masses m1 is equal to 12 kg and m2 is equal to 8 kg. So m1 is equal to 12 kg and it is the m2 is equal to 8 kg is here and thereafter are attached to the ends of a cord which passes over a pulley of an Atwood's machine. The masses of the pulley is m is equal to 10 kg and its radius is the 0.1 meter. So, and it is the m is equal to 10 kg and again radius is the 0.1 meter, radius is equal to 0.1 meter and thereafter calculate the tensions in the cord and the acceleration of the system. So, that's why it is a calculated tensions in the cord and the acceleration of the system. So, there are slight mistakes are there in that printing. So, now it is the tensions and again the acceleration of the system. So, Atwood's machine means, so the arrangement of Atwood's machine is here like this. In this case, m1 is equal to 12 kg. It is a m1 is here, it is a 12 kg and m2 is here. m1 is equal to 12 kg and again the m2 is here. And this is the capital M. Its radius is the 0.1 meter. And it is the capital M is here. Now you are supposed to find out what are the accelerations, the tensions in the cord and the acceleration of the system. Tensions in the cord and the accelerations of the system. Now definitely the tensions will be different. T1 is here and again the T2 is here. Why? Because here the mass of the pulley is considered. When you are not considering that mass of the pulley, then the tensions will be same for the same string. Suppose in Newton's laws of motion, in that entire Newton's laws of motion, we did not take the two different tensions for the same string. For the same string, we have taken only that same tension is there. But here the mass of the pulley is considered means definitely it will be a different values, T1, T2, and the difference of these two tensions that makes that is the force, that is the force which rotates this pulley. That's maybe in the clockwise or the anti-clockwise that rotates that pulley. So that's why it is that the difference of these two tensions, if at all these tensions are same, then there is no need for this pulley to rotate. So that's why here the tensions are different. Now here T1 minus T2 is the force which causes the rotation of this pulley, that is the T1 minus T2 into R is equal to I alpha. This is the formula here. T1 minus T2 into R is equal to I alpha. And here that T1, this is the basic equation to find out that either that accelerations or whatever it may be, it is the tensions developed in the string. T1 minus T2 into R is equal to I alpha. Here the T1 is equal to, so it is coming down. It is coming down because of its more mass. That's why it is coming down with the acceleration A, and again it is the A, and that will be the common acceleration because it is a connected body. It is a connected body, so that's why it is the A is here. T1 is equal to m1 of G minus A, and T2 is equal to m2 of G plus A. As I already told you, you don't frame the equations, that is the MA is equal to T1 minus m1G. You need not apply all those equations. So it is just a general formula. When the elevator is coming downwards, the apparent weight of the man is given by that m of G minus A. When it is moving upwards, apparent weight of the man is the m of G plus A. You apply the same equations even in the case of the strings also, that is the tensions developed in the strings also. m1 of G minus A, T2 is equal to m2 of G plus A is here. And now here from 1, when you are applying alpha is equal to, already you know, it is the A by R. Alpha is equal to A by R. You have to apply all these, and again the I value is not directly given here, so that's why I have to find out. As I already told you, this is the pulley is nothing but the circular disc which is to rotate about its natural axis. So that's why I is equal to mr square by 2. I is equal to mr square by 2 is here. You have to apply all of them here. So from 1 that is the T1 minus T2 means m1G minus m1A, m1G minus m1A, and again the minus T2. Minus T2 means it is the m2G and minus m2A into R is here, into R, and thereafter that is the LHS part is completed, and I alpha is the mr square by 2, and alpha is the A by R is here. Now this is our target is to find out the acceleration. Our target is to find out the accelerations. That's why we have to bring that acceleration here. It is the R is equal R of, and it is the m1G minus m2G. So it is the G of. Now that R also will be cancelled on both sides. So that's why it is the mr square. It will be the R only, and that R also will be cancelled. So it is the G of m1 minus m2. G of m1 minus m2, similarly minus A of m1 plus m2. Already this R is cancelled to this one, and again that R is cancelled to this one. So that's why it is the MA by 2. MA by 2 is here. And thereafter now we are bringing that all that accelerations on one side. So it is the MA by 2. M by 2 is here. A can be taken like this. A of m1 plus m2, and again the plus m by 2 is here, and thereafter it is the G of m1 minus m2 is also there. G of m1 minus m2. And when you are taking that A is equal to G of m1 minus m2 and by m1 plus m2 plus m by 2 is taken, and when you are applying all those values that you are given in this problem, when you are applying, you are getting that acceleration also. After finding this acceleration, you have to apply this acceleration here. Then you get those tensions also. T1 is there, and again the T2 also you can get. So once again I tell you how to solve such type of models. So in this problem you won't be given any figure. Atwood summation means from that you have to understand how to draw that figure. So this is the figure m1, m2. m1 is the higher dominating mass. So that's why the acceleration will be like this. Now here you have to frame the equation. The difference of these two tensions make this pulley to rotate. So T1 minus T2 into R is equal to I alpha, that is the first one. And T1 is here, that is the first one. T1 is equal to, as it is coming downwards, m1 of G minus A. T2 is equal to, as it is moving upwards, m2 of G plus A. Alpha is equal to A by R. And I is equal to mr square by 2 for the pulley. You apply all of them here. Then you frame the equation, ultimately you frame that equation for that A, and A you apply those values, then you get that acceleration. And after finding this acceleration you apply that here, then you can find the tensions also. So now today these are the problems we are going on this moment of inertia, and thereafter in the next class also we continue some more problems. Thereafter I start that conservation of angular momentum. In the next class, conservation of angular momentum. Thank you, students.